Bismillahirrahmanirrahim. So, dear students, let's see problem number 5.11. And this problem gives us two perfectly conducting cylinders. Cylindrical surfaces of length L are located at rho equals 3 and rho equals 5 centimeters. The total current, the total current passing radially outward through the medium between the two cylinders is 3 amperes DC. Okay, this is something which has been given to us. In part A, we are asked to find the potential difference, find the voltage and resistance between the cylinders, and electric field intensity in the region between the cylinders if a conducting material having conductivity of 0.05 Siemens per meter is present between the two cylinders. So this value of sigma, which is 0.05, gives us a hint that the material which has been placed between the two cylinders is definitely not a good conductor. Rather, it must be some insulator in between the two cylinders. So the diagram has been shown here. Two cylinders, inner one with radius rho 1, the outer one with radius rho 2. Let me see, confirm whether it is radius or okay, radius is given to us. All right, so if you want to see the top view, this is the top view. Inner cylinder radius 3 centimeters, outer cylinder radius rho 2 meaning 5 centimeters, and there is a current which is flowing radially outward from inner cylinder to outer cylinder, and the value is 3 amperes DC. This is given to us. So this is the current, not current density. Okay, 3 amperes is given, and conductivity is also given to us, and the height of this cylinder is L, length of the cylinder, and we are asked to find V, potential difference between these two cylinders. So let's solve part A first. So V naught is nothing but minus E dot dl. All right, from inner cylinder to outer cylinder. It means that we have to find E first. To find E, if the voltages were given to us, we could have used this expression to find E, but since the equipotential surfaces are not given to us, we are actually required to find that. So the other expression which we can use is the relationship between E and J, but again J is not given to us, but the current is given to us. So current density is nothing but total current divided by area of the cylinder, because it is radially outward. The area which the current will see will be these cylindrical areas, cylindrical surfaces. So the height is L. The circumference of the cylinder is given by 2 pi rho. So if we want to find current density on the inner cylinder, we'll just replace rho to be 3 centimeters. If we want to find the current density on the outer cylinder, we'll just we'll just replace rho to be 5 centimeters. So since L is not given to us, so current density in both the cases, either inner or outer, will be in terms of per unit length. All right, so this is the magnitude of current density, current divided by the surface area which is seen by the current. So the total current flowing between this point to that point is radially outward All right, coming out of it may be imagined as if the current is coming out from the inner cylinder and reaching the outer cylinder. So while coming from the inner cylinder, the area, the total area which the current is seeing is 2 pi 3 centimeters into L. Okay, and as soon as the current reaches the outer cylinder, the total area which the current is seeing is 2 pi 5 centimeters multiplied by L. So this 2 pi rho is nothing but the circumference, and the L is nothing but the height. So total area is given by definitely circumference by height. Area of the cylinder formula is given here. So this is the magnitude of current density, and the direction of the current, since it is radially outward. So the current density is actually radially outward, meaning it has got this this component only. So from here we can find electric field intensity to be this 3 upon 2 pi rho L times this point divided by 0.05. So 0.05 okay. So if you multiply it by 2, it will be 0.1. If it is 0.1, so it will be 30. So 30 upon pi rho L. I hope I'm doing everything correctly and not missing anything. So this is electric field intensity. Now we can use this expression to find potential difference. 30 upon pi rho into L. A rho is E, and dl if you move a jet charge from here to here, this is the direction of J, not only J but also E. So you can consider these arrows to be direction of E as well. So if you take a jet charge from here and move it in this direction, okay, so the amount of work which you'll do from here to here will be the potential difference. So dl will be rho d rho a rho. So d rho a rho, starting from head of the electric field towards tail of the electric field. Starting from head of the electric field means 5 centimeters. 5 centimeters to 3 centimeters. Do the maths now. Minus 30 out, pi out, dot product will be 1, L out. With an integral sign, what's left? D rho upon rho, from 0.05 to 0.03 equals minus 30 upon pi L ln of 0.03 minus 0.05 or 0.03 divided by 0.05, which is equals to minus 30 upon pi ln 3/5. Definitely ln of a negative entity is going to be a negative entity. Negative is going to be positive. So after you evaluate this, you are going to get the potential difference to be 4.88 upon L, potential difference, which is V naught, is going to be 4.88 upon L. So this is actually the potential. If you increase the length of the cylinders, the potential difference is expected to decrease. Okay, if it is so, then the potential difference, if it is a coaxial cable, remember I did an example of coaxial cable. The longer the cable, this expression tells us that there will be lesser potential difference between the inner core and the outer shielding. And if that's the case, there will be less stress on the insulating material between the inner cylinder and the outer cylinder. So there will be lesser current density. Interesting. So this is, you see how we can design a good coaxial cable, keep the length as much as possible, so that the potential difference between the two cylinders would be as small as possible. Try to make it negligible. Doing so will reduce the leakage current from the inner cylinder towards the outer cylinder, because less potential difference between these two cylinders means the insulating material between these two conductor planes or surfaces will be in lesser stress, lesser electrical stress. Anyway, so let's move towards the second thing, which is resistance. By the way, we have already found electric field intensity. So actually, this is also our answer. This is also our answer, and we have to find R, which is resistance between the two surfaces. So that's quite simple. We know that resistance is V naught divided by I. V naught is already given to us. I is already given to us, but V naught is not. So V naught we have already found out. So 4.88 divided by 3 L, this much ohms will be the resistance. This much ohms will be the resistance. So it will be 1.63 ohms. So 1.63 divided by L ohms. The larger the value of L, the smaller the resistance of the whole setup. So if you would inject some anyway, let's leave that discussion. In part B, however, a very interesting thing is being asked out. It says that show that integrating the power dissipated per unit volume over the volume gives the total power dissipated. Okay, so definitely the volume which is between the inner cylinder and the outer cylinder, the total power dissipated within this region, the region which is between the inner cylinder and the outer cylinder, per unit volume. So there I am using a formula, and we can talk about the proof of this later on. The potential, the power dissipated per unit volume, this is capital P, power per unit volume, can be given as the dot product of E dot J. How? We can talk about it in some other session. So this is the amount of power which is dissipated within this material between inner cylinder and outer cylinder per unit volume. at the minuscule, at the point level, this amount of power will be dissipated. So the total amount of power, if we integrate, the differential amount of power which is being dissipated throughout this material and integrate all those differential contribution to power, we'll get the total power which will be dissipated between these two conducting surfaces. Doing so, actually, to do so, we'll have to integrate this. Okay, so to integrate this, we just have to cross multiply first, and then we'll have to do this integration to get the total power dissipated within the insulating material between the two conducting surfaces. Definitely, this is total volume, volume integral. Okay, so at point level, at differential level, within that insulating material, the power is being dissipated as per this formula. This is a standard formula. At each point, this much amount of power is being dissipated. To find the total amount of power which is being dissipated throughout the bulk of the material, you'll have to integrate it. So electric field intensity, we already found out that to be 30 upon pi rho L aero. Take the dot product with respect to J, 3 upon 2 pi rho L aero, and we'll have to integrate it. Okay, this is, and for this kind of cylindrical material, we all know that the differential volume is rho d phi dz, and differential volume is definitely a scalar quantity. So volume integral, take the dot product and drag all the constants out. So 90 in the numerator, and denominator will be having 2 pi square and L square, L being the constant. So in the integral sign, we are going to have rho square into rho, so we'll be having rho this. Taken out, rho square is left, which will be cancelled with this rho, and 1 upon rho will be remaining. Okay, so 45 upon pi square L square integral d rho upon rho integral d phi integral dz from 0 to L, the height is from 0 to L, and phi from 0 to 2 pi, and rho from 0.0 3 to 0.05. Okay, this is the, so we've got I already and V not already, so this is something which I can conveniently remove from here to make space for us. Alright, so we are talking about power, total power dissipated, and 45 upon pi square L square and ln of rho, put the limits 5 upon 3 times 2 pi times L. So this L will cancel out, will cancel this L square but not whole. So this pi will remove this. We are going to have in the numerator 90, and the denominator pi L into ln point beta 3. 90. All right. So this is what we are going to have. Let me check what this would come out to be. This would come out to be 14.64 upon L. 14.64 upon L watts. This is how we get this. Power dissipated, integrated, the contribution, total power dissipated got through the integration of the power dissipation at each point within the volume. And this, by the way, this answer can be cross-checked because we have to show that this is the correct power dissipation. How we can show that? We can show that by using our typical formula. V naught is 4.88 upon L, and I is 3. So had there been 5, had this been 5, we would have got 15 upon L. Had this been 4, we would have got 12 upon L. So since this value is not 4, not 5, but a value which is closer to 5, so definitely we are going to have a value which is closer to 15. So if you would multiply, you will get, use your calculators if you don't want to use your common sense. You are going to get the same answer. So it has been shown that the power dissipated at each point within the volume, if integrated, will give us the actual power which is dissipated throughout the volume. So this is how you are going to solve this problem. I hope this would help. With this, Assalamu alaikum.